Okay, we're going to start here with some information from Chapter 20, A and B. Some of the stuff I do in this section will end up with shortcuts later on that'll help us out a little bit. So near the end, if you get a little confused with some of the math we're doing, just, it'll be all right, and we'll kind of come back to it in 20, C and D, and hopefully give you another strategy to do that. So we start Chapter 20 by talking about rates of change and rates. All a rate is a comparison between two quantities using division. So a comparison So we're talking any type of rate of change. In Algebra 1, you talked about a lot of different slopes, and slope is an example of a rate of change. Some units you might see miles per hour we're used to. Since IB is an international program, we also deal with maybe kilometers per hour or maybe per minute. You'll also see notation where they abbreviate the per, and so kilometers per liter could be written as kilometers and then liters to the -1. The -1 exponent just implies that it would get flipped to the bottom of the fraction. That's the per. Per is just another name for, another way to say division. So points per game is an example the book uses, so anything with the word per. In our first example, we're looking at words per minute. We're looking at errors per minute, errors per word. And these are ways to describe how these people are doing what they're typing. So it says, Joseph typed 213 words in 3 minutes and made 6 errors. Marie typed 260 words in 4 minutes and made 7 errors. So just looking at the numbers, it's hard to compare because Joseph typed for less time than Marie did. So really, Marie typed more words, but it also took her more, she took 4 minutes. So we want to be able to have a way to compare these to kind of scale them down. How many words do they type in 1 minute might be a question. So if we compare their words per minute, for Joseph, he typed 213 words, and that happened in 3 minutes. So we take 213 divided by 3, and he's 71 words per minute. If we do the same thing for Marie, she typed 260 words in 4 minutes, which gives us 65 words per minute. So this tells us that Joseph is a faster typer. He typed 71 words per minute, every minute. Now, we have to be careful with rates because that does not mean that Joseph typed 71 words the first minute, 71 the second, and 71 the third. That means that overall, for the 3 minutes, he kind of averaged 71 words per minute. Maybe he started out typing really fast, and then somewhere in minute 2, he got a hand cramp, and he had to stop for a second, right? And so then he slowed down, and then he started picking it up again. So there could be very much a change in how fast Joseph is typing, but of course, over the course of these 3 minutes, he typed 213 words. So it gives him an average words per minute of 71. We could also look at something like errors per word to compare these people's typing. So if we look at the number of errors Joseph had, he had 6 errors out of 213 words, which gives an error rate of 0.028. That means that he has 0.028 errors per word. It's a pretty small amount. If we look at Marie, she had 7 out of 260, so her error rate is similar to Joseph's, 0.027, but it's a little bit smaller. In this case, we want a smaller number. Errors per word. The less errors per word, the better. So hers is a little bit better as far as the number of errors that she made. So we could summarize, Marie was slower, but made fewer errors per word. So whenever we're talking rate of change, it can be constant or it can be variable. So the idea of a constant rate of change is, if we think about Joseph and his 3 minutes, he could have typed exactly 71 words each minute. So for 3 minutes, he could have typed 71 words, 71 words, 71 words for all 3 minutes. That would be a constant rate. He had a constant rate of 71 words per minute throughout the whole thing. Alternatively, he could have typed considerably more words in the first minute, maybe fewer in the middle, and then an average amount at the end, averaging him to 71 words per minute. That would be variable. For a constant rate of change, you've dealt with a lot of constant rates of change. This would form a straight line, where our variable rate of change is some type of curve, or it could be a collection of straight lines. So a constant rate of change, if we think about time and distance, if you're going on a trip, some time has passed and you've traveled a certain distance. So it might look like this. So when time is 0, you haven't gone anywhere. Maybe time is 2 hours, you've gone, 70 miles or something. So this would be a constant rate of change. This would be like if you got on I-44 and set your cruise at 70 and then didn't touch it. You had a constant rate of change the entire time. You went 70 miles per hour. A variable rate of change is a little more useful, because very rarely do we have situations where you just get in the car, set it to 70, and don't stop. Typically, you go through a town, you have to slow down, you stop at the gas station to get a drink and fill up your gas tank, maybe you, stop to get food, and that type of thing. So maybe you start out with your cruise control on, and then you stop for a while and no distance is traveled. You stop, you get a snack, and then maybe you kind of speed up slowly and then faster and faster and faster. I don't know, making something up. So this is the idea of a variable rate of change. It's not constant, it changes. It is constant right here because you're going 0, constant, but then it's accelerating. It has a curve to it at the end. So for a straight line, our rate of change is just the slope, or the gradient. So IB likes to use the word gradient. It's more of a universal word. We tend to use the word slope, but a straight line has a constant rate of change over that time. So this would be maybe constant 70 miles per hour, something like that. A curved graph, in order to find the rate of change, we just have to work with averages right now. So you can find the average rate of change by finding the slope between 2 points. So as a reminder of our slope formula, we tend to use the letter m, y2 minus y1 over x2 minus x1. This is our slope, our rate of change formula. So let's look at how this works with this curve at the bottom. It says the number of mice in a colony was recorded on a weekly basis. Estimate the average rate of increase in population for the period between 3 and 6 weeks, and then over the entire 7-week period. And then which week had the greatest rate of change. So we're going to start by looking at the average rate of change from 3 to 6 weeks. So I'm going to identify how many mice we had at each of those weeks. Since we are only given a graph, we have to do a little estimating here. So at 3 weeks, there's our dot, and at 6 weeks, there's our dot. We want the average rate of change. You can tell it's variable because it has a slight curve to it. So the rates, it looks a little slower here, and then it gets a little steeper and a little bit steeper. We just want the average of that time period. So we're going to look at the slope of the line if you connected those 2 points. This is just like slope when you did this in Algebra 1. You also did slope in geometry. It's just now we're having to pick these points off of a curve. We're still just finding the slope of a straight line. So I'm going to have to guess this point. I'm going to go with 3 weeks and maybe 110. 105, 110. I'm going to go 110. Okay, estimating. It's, of course, an estimate, so you could use something different. It'd be a little bit different. I'm going to estimate this. This is 6 weeks, and how about 240? It's a little under 250, so I'll go with 240. To find the slope, we do y2 minus y1 over x2 minus x1. So I'm going to do, my slope is y2 minus y1 over x2 minus x1. My y's are the larger numbers here, xy, xy. So it's 240 minus 110 over 6 minus 3. So we end up with 240 minus 110 is 130. 6 minus 3 is 3. Got something different in my notes. I think I made a mistake. So 130 is right, 3 is right, so we end up with 43.3. It's important in a word problem to take note of what the units were. So our units here, we had y's on top. Our y's, our y's, is population size. So this is number of mice. Our value on the bottom is x, which is in terms of weeks. So our 43.3 would have the units of mice per week. So what does that mean in terms of the problem? Well, that means that between the weeks of 3 and 6, between weeks 3 and 6, we added, on average, 43.3 mice per week. Of course, we did not add 0.3 of a mouse at any point. These are whole mice. This is an average. So over the course of those 6 weeks, we added an average of 43.3 mice per week. Over the 7-day period, we're going to do the same thing, except for we're going to use our starting point and our ending point. This is over the course of the entire experiment of measuring this mice population. So if I connect those with a line, I'm looking at the slope of this line. So for my 7-week period, this first point looks like 0.50, and my last point, it's a little over 300, maybe 310. Okay, once again, you have to estimate. And we're going to subtract our y's on top, so 310 minus 50, and our x's on the bottom, 7 minus 0. 310 minus 50 is 260 over 7. So this is 37.1. And once again, our units on the top were mice, and our units on the bottom were weeks. This is 37.1 mice per week. So our rate of change between 3 and 6 weeks was greater than our average over the entire course of the experiment. That's due to the fact that it was slower here. So it was slower here, and then it sped up. So when we are calculating the rate of change just between these points, we were only looking here, but now we included all these slower rates of change down here for the entire thing. It says which week has the greatest rate of change in population. So we're looking at where is it increasing the fastest, the greatest rate of change. And so this would be the final week, has the steepest line. And that kind of makes sense for mice populations. They multiply very quickly. And so put between 6 and 7 weeks. Okay, this covers 20A. I'm going to go ahead and pause here, and then I'm going to pick up a second video to cover 20B.